So, so I'm going to talk about sort of very simple and sort of model or system, and there is a sort of interesting first order phase transition there. So this is the sort of work done which was done with Giacomo Gradenigo, who is now in Rome, University Sapienza. And so the model or system that I'm talking about is just a run and tumble particle. So many of you have heard about this. So imagine that this is in 2D, let's say. So you have a particle. So this particle, with a random velocity chosen from some distribution P of V, it just moves ballistically. And during an exponentially distributed time, which is drawn from some exponential distribution, with gamma inverse as the sort of persistence time scale, because it persists in that direction during that. After that, the particle tumbles and chooses again fresh sort of another velocity and moves in that direction, and it continues like that. Okay. So this is actually called the persistence random walk, which was studied quite extensively in the 80s, and then later rediscovered in the active, literature, active system literature as an untumble particle. And this is a very simple sort of interesting model. And only input different from normal diffusion is that you have a time scale here, which retains the memory. So this is the run and tumble particle. Now I'm going to look at a system which is even simpler, which is in one dimension. Okay? So in one dimension, so you just, again, the particle moves on a line. And so this is the space, and this is the number of steps. It chooses, I'll take just a simple case of Gaussian velocity distribution. And I set gamma to be 1. The time duration is actually, taken from an exponential distribution. And I know this is the typical trajectory, for instance. And I also put an external field E drive, but that's not really necessary, but just for completeness. So what happens is that at each run, so the particle moves according to Newton's law. So this is the Vi, is the velocity of the ith run, times tau I, the duration. So this is the distance, plus E times tau I squared. So this is just basic Newton's law. So this is the distance covered by the ith run. Okay, and so the position of the particle after n steps is just the sum of xi. Each of them is independent and identically distributed random variable. So what can be simpler than that? So just looking at the sum of IID random variables, each of them is drawn from a distribution which is given by this object. These are two random variables, tau I square also. So you can compute, given these two input, you can compute the distribution of P of xi, and it happens to have a stretched exponential distribution. And you're asking, so the question I'm asking is, what is the position distribution after n steps? Very simple problem. And even this simple problem has a phase transition. Okay, so that's the sort of interesting thing here. Now, when you talk about phase transition, you have to tell me what are the phases and what's the control parameter, right? So let me just tell you what is a phase and what's control parameter. So what I'm plotting here is P of xn, the position distribution after n steps versus x. Okay. So this is a sum of IID random variables. So all of us know that there'll be a central limit theorem. So around the average, it has a Gaussian distribution. Okay. Now there are 3 regimes here, 1, 2, and 3. So I'm looking at P of xn this as a function of x, and this x is like my control parameter. So what happens if you look at this PDF of this distribution is that there are 2 non-analytic points. One is at minus xc and one is at xc. And this is kind of not symmetric because of the drive E, but more or less similar physics here. Okay? So what happens here, that if you're x, if you set your distance x to be between minus xc to plus xc, and this is typically of order n to the power 2/3. So in that central regime, if you look at a trajectory, you will see that each jump is more or less of the same size. And this system is sort of democratically, this total sum is just composed of individual sums which are more or less almost of the same size. Now what happens when x is bigger than this critical value xc, that means we are looking at this tail over here. So n minus 1 steps of size of order 1, there's one big guy which forms, which we'll call the plus condensate. So that means if you look at the runs, there's one run which is of the order of system size. This is exactly similar as in the Bose-Einstein condensation, for instance. So there's one big run, and which is going in the positive direction. And if your x is less than minus xc here, then you have a negative run, again exactly similar physics. Okay. And so this change of behavior, the condensate starts forming exactly when you tune your capital X, if you're asking tail of the distribution at this critical value xc. Okay. So this problem you can solve exactly, and I'm not going to go to the details, but what happens is that, essentially you have to solve a saddle point equation, and what you find is that there is a saddle point as long as your x is between minus xc plus xc, and in particular near the peak here, you have a Gaussian distribution. So let's go on this side only, because the physics on this side is more or less similar. If you go on this side, so there's a Gaussian distribution over this range here, from the average value to till xc. And then when this distance from the average is of order n to the power 2/3, you are at this point, then it has a different behavior. It has a large deviation behavior, which is exponential minus n to the power 1/3 times some non-trivial function of this scale distance, z. And if you go very far away, the x is extremely large, then of course, it's just totally controlled by one condensate, and you get a stretched exponential distribution. Okay? So this change of behaviors from this regime to the extreme tail regime, intermediate regime, if you go near here and zoom out this regime, so then you see this when x minus en is of order n to the power 2/3, that means you zoom out this regime and you get a non-trivial intermediate large deviation function psi of z, which if you plot, what you see is that it's a Gaussian till a critical value of zc, which actually you can compute. And so there it's like a z square, and then it changes to a different form as you increase beyond zc. And if the large deviation function itself is continuous, but its first derivative is discontinuous, which is a hallmark of first order phase transition. And this is, you see, is numerically. So if you plot psi prime of z, derivative versus z, so as your system size increases, you see that you develop this discontinuity as n goes to infinity. Okay? So in that sense, it's a first order phase transition. So let me just summarize and conclude. So basically, so essentially you have two things here. And if the external field E is 0, qualitatively the physics is same, it's symmetric. And this regime, instead of n to the power 2/3 here, it becomes n to the power 3/4. But once again, you still have this condensation transition, and you have the first order phase transition. And so this first order phase transition basically separates a region of typical fluctuations to very large atypical fluctuations. And it can actually happen not just for Gaussian distribution. Any distribution which has a width, finite width, you will actually get this condensation transition, except if you take a constant velocity, because there is no width here. Width is 0 if you have a delta function. In that case, you would miss this condensation transition. Okay? And of course, what we're looking at now is what happens in higher dimensions. I believe that this will persist even in higher dimensions. There will be always a big run, essentially, in the condensate phase if you look at the tails. So just to summarize, sum of random variables, we all know that, you typically say that, okay, as long as the variance is finite, you will always have central limit theorem. But central limit theorem just tells you that only near the peak, you will have the Gaussian distribution. If you go away from the peak and you explore regions which is larger fluctuations, you can have actually non-trivial tails and phase transition, real phase transition, thermodynamic phase transition. And this is, you can actually compute by just computing large deviation functions, because that's the analog of free energy. Okay, so I think I've finished much before my time. Thank you.
So Satya, if PFV has major tails, if it's a Lorentzian or something, do you know anything about what might happen?
Yeah, no, if you have a power law tail, then of course, again, you will have condensation. Because, this happens, again, you can ask these more general mathematical question, right? So if you have a set of n random variables, you give me the distribution of each variable, okay? Yeah. So when do I expect condensation? Okay, so you would expect condensation as long as the P of x, it has a tail,
as any kind
which
of
is between 1 over x square and exponential. So stretched exponential, in this case, it happens that if you choose the velocity as Gaussian and the time duration as exponential, look at the product actually is stretched exponential. So it's actually precisely in that range.
Nice.
So.
My question was that this is of course done in one dimension, but
Yes.
are there real physical systems where such signatures been observed?
No, I mean, I'm telling you, this is run tumble particle. It has been studied quite active, quite
Bacteria,
extensively in the active literature now. E. coli bacteria, for example, in 2 dimension. So that does exactly this run and tumble dynamics. Okay. So what I'm saying is that if you take this run and tumble particle and just look at the end-to-end distance distribution, and look at the tails, and you would see that there is one run which dominates over the other guys. Okay.
Persistence, yeah.
No, not persistence length. One run which is very big. You have n runs. Just look at your sample, and you will see that the one guy actually, one Bill Gates basically. Okay, the rest are all poor guys. Okay, so this is what happens.
So, what does it have to? I mean, what our general understanding that you cannot have phase transitions in one dimension.
No, this is not. This has nothing to do with magnetic systems or something like that. This is just a phase transition. When we say, I mean, you can sort of, the way to define, this here, the way I'm defining phase transitions is, in these systems is through the large deviation function. That is, if you look at the large deviation function, okay, the probability distribution tail, so that large deviation function is typically sort of behaves like the free energy in systems. Okay, so here, I mean, this is not a short-range system, or it's not a magnetic systems, or things like that. There's, this is just a sum of
you think there's no conflict in sort of calculating the entropy of a one-dimensional system and having singularities?
Systems you can have phase transitions. Okay, it's not, this is a sort of old concept that, I mean, that if you have a short-range order, that this comes from magnetic systems. But now we know that in many statistical mechanical systems in one dimension, you can have phase transition even without long-range order.
Yeah. So, so could you just comment on the role of the thermodynamic limit here? Because
sorry, where?
Yeah.
Sorry, yes.
Okay, sorry.
Yeah.
So because it seems to I don't know, I didn't get everything.
Yes.
But because as n tends to infinity, the transition seems to disappear or something.
No,
right?
it doesn't disappear. It becomes. I'm plotting the psi prime.
Okay.
Psi prime z. It actually develops the singularity. The transition, as in any thermodynamic system, I mean, any physical system, it happens only in the thermodynamic limit.
So how was that happening here? That was not very clear. Okay, sorry.
No, so in the sense, I'm saying, okay, so if you look at the distribution of this guy, right? So if this is the plot here. If you look at around this xc, which is, just basically x minus en of order n to the power 2/3. This is the En. So if you zoom in this regime and you look at the form of your distribution, you just examine your distribution there, okay? So you will find exponential minus n to the power 1/3 into some function of this z, and z is just x minus En divided by n to the power 2/3. Psi is inside the exponent. Okay. So in that sense, see, normally when you write down in the typical StatMech system, short-range system, you write exponential minus n into something. So this is like a partition function, and this is like a free energy. Okay. So these singularities of this large deviation function is actually what signifies phase transition. Okay. They're much more general than what we usually say in statistical mechanics. That in statistical mechanics, I mean, we write, z, which is the partition function, as exponential volume times the free energy, right? Free energy, which can be a function of some parameters. Okay. So V is like n here, but now you know that in many systems, I mean, it's not always scales extensively, but it can behave like this. Yes. And so singularities of this function, which is sort of analogous of this function, that describes the order of the transition.
So the confusion was that there is an n in the psi itself, which is normally not what one sees.
I'm sorry, maybe we can carry on
N? No, this is
during lunch.
No, okay.
Let's thank the speaker again for a nice talk.